Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my 12th video on my series on algebraic number theory. And this is also my second video in my sub-series on rings and ideals. And this is going to be a very short video, very short and sweet. I'm just going to prove one thing in this video. I already talked about Euclidean domains. I talked about that a few lessons ago. I also talked about principal ideal domains in my last lesson. And what I'm going to prove in this lesson is that every Euclidean domain is also a principal ideal domain. And this is going to turn out to be a very useful result because we already showed that, the Z of I, the ring of Gaussian integers, is a Euclidean domain. So it'll follow right away that it's also a principal ideal domain. And the ultimate goal is to show that the Gaussian integers is also a unique factorization domain. It also turns out that every principal ideal domain is also a unique factorization domain. But that's a much harder proof. That's going to take a little bit more machinery. So I'm not going to prove that part today. But I will prove that the Gaussian integers is a PID. So anyway, let's begin. So I'm just going to review a couple definitions to begin with. An integral domain, I probably should have stated this in the last lecture. Integral domain is a ring such that for every pair of elements A and B in the ring are such that AB equals 0, that means either A equals 0 or B equals 0. And a generic example of that is the ordinary integers. As a matter of fact, the ordinary real complex numbers, any kind of numbers that you guys have probably studied, it's true that if you have a product of two numbers from that domain that's equal to 0, then at least one of those numbers has to be 0. But there are certain rings that are not integral domains. I think I gave an example last time, Z modulo of 6. Z modulo any composite number, it turns out, is not an integral domain, but Z modulo primes are. Anyway, and it also turns out that the Z of I, the ring of Gaussian integers, is an integral domain. I mean, yeah. And then the second definition, Euclidean domain, I also defined this a few lessons ago. I'm going to define this definition is going to look a little different, I think, but it's the same definition I gave before. So Euclidean domain is just an integral domain with a particular function defined over, and this function is called the Euclidean norm. And a norm is just a function from the elements, the non-zero elements of the ring to the natural numbers. And usually norms are multiplicative. They don't have to be. For what we're doing here, Euclidean norm doesn't have to be multiplicative. But so it's enough that here's the definition of Euclidean norm. So you take any two elements A and B of your ring, but B has to be non-zero. That means there exist other elements called Q and R, and you're supposed to think of Q as the quotient and R as the remainder. So that what that means is that we can say A equals QB plus R. So A is Q times B. That's why we call Q the quotient, and the remainder is the thing that's left over, R, and the remainder could be 0. If it turns out that A was a multiple of B, then you just have A equals QB. That's probably the least interesting case. But if you have a remainder, what has to be true is that the Euclidean norm nu of R has to be strictly less than nu of B. And you're probably familiar with this. I mean, like I said, the ordinary integers is the Euclidean domain because nu is just the absolute value in that case. And then, or it could be the square of the absolute value, I guess, if you want to make sure that it's non-negative. Um, well, actually, absolute value is not negative, so that doesn't matter. But it could just be the square of the integers if you want it to be a. Anyway, so and then the Gaussian integers is also Euclidean domain. If we let the norm again be the square of the absolute value, so for instance, if and we remember we called those norms n instead of nu. It doesn't really matter what letter we use, but norm of ordinary integer a is a squared, or n is n squared, and then if you want to generalize the norm to Gaussian integers, you just say the norm of a plus bi is a squared plus b squared. And obviously, a squared plus b squared is a non-negative integer, for every pair of integers a and b. And also, I think it's pretty easy to see. I mean, we proved that the Gaussian integer is the Euclidean domain with this norm. I did that a few lessons ago. It's not a very easy proof, but I did prove it. So I'm not going to prove it again. So we do know that both the z and z of I are Euclidean domains. And now, this is the icing on the cake. This is really the heart of today's lesson. I'm going to prove a theorem that says that every Euclidean domain, which I'm abbreviating as ED here, is also a principal ideal domain, which I'm calling PID. So every ED is a PID. And it's not that hard to prove, it turns out. So here's the proof. So let's let R be an arbitrary ED, an arbitrary Euclidean domain, with a norm nu, and is a Euclidean norm. That's all we care about. This thing we're calling nu is the Euclidean domain, norm of this Euclidean domain R. And we're letting I be an ideal of R. And I defined ideals in the last lesson. Maybe I should define them again in this one. But if you don't remember what an ideal is, then just go back to the last lesson. But we're assuming I is now an ideal of R, and we want to prove that I is a principal ideal. That will prove that that R is a PID, because it proves that remember, a PID is an integral domain such that every ideal is a principal ideal. In other words, every ideal is generated by one element of the ring. So that's what we want to prove. So how do we do this? Well, we take any two arbitrary elements of I this time. We're calling them A and B. And since I is a subset of R, that means that A and B also belong to R. And that means since it's a Euclidean domain, that means there exist elements Q and R, little r of capital R, such that A equals QB plus little r, and furthermore, either R is 0 or the Euclidean or nu of R is strictly less than nu of B. And so let's look at the first case first. That's easy. Or actually, let's assume that R is non-zero. We'll get a contradiction if we assume that. So the other thing I forgot to mention, it turns out that Q and little r have to belong to the ideal. And the reason that's true, well, actually Q doesn't, but little r has to belong to the ideal. Why is that true? Well, QB belongs to the ideal because remember, B belongs to I, and one of the properties of ideals is the black hole property. If you start with any element of your ideal, in this case B, which we're assuming was an element of the ideal I, that means any multiple. If you take any element Q of R and you multiply it by B, you're still going to get an element of your ideal I. So that means that QB belongs to I, and we assume that A belonged to I. And now let's look at the difference, A minus QB. Another property of ideals is if you have any two elements of an ideal, the difference also has to be an element of that ideal. So that means that R, which we can also write as A minus QB, that must also belong to I. So we just concluded that this element R, this remainder, must belong to our ideal. But now let's assume that little r is non-zero. And what does that mean? I mean, the other thing I forgot to mention, I'm kind of jumping the gun here, but we're also assuming that little b is an element of the ring R of minimal norm. This is a critical assumption. I forgot to mention this one. And we know that such an element must exist because the norm is defined over the natural numbers, and since the natural numbers has a minimal element, namely 0, that means that any function whose image is the natural number, that function, what do you call it, the domain of that function also has to have a minimal element. So that means there has to exist an element B of our ring R such that the norm of B is minimal. Either B is 0, and the Euclidean nu doesn't have to be defined for 0. Nu of 0 doesn't have to be defined. But so that means that either B equals 0 or nu of B is minimal. And but now we're assuming. Remember, we said that if we assume R is non-zero, well, since this is a Euclidean domain, that means the norm of R, nu of R, has to be strictly less than nu of B. But that contradicts our assumption that nu of b was minimal. So the only way this can happen, the only other possibility is that r is 0. But if r is 0, that means that a equals qb. That means that a, which was an arbitrary element of our ideal, that has to be a multiple of b. That means that a has to belong to the ideal generated by b. And that means that since b was an arbitrary element of minimal norm, and a is an arbitrary element of our ideal, that means that the ideal has to equal, it has to be generated by b. That's kind of an interesting fact. So not only is it true, since there's one generator, that proves that it actually proves our theorem, because we just showed that I equals the ideal generated by any element of minimal norm. So that means it's a principal ideal in particular. So that completes our proof. That proves that every Euclidean domain is also a principal ideal domain. In particular, the ordinary integers is a PID, and the Gaussian integers is a PID. And we're going to see a lot more examples of PIDs as we go on. And like I said earlier, it turns out that every PID is also UFD, unique factorization domain. I'll prove this later. I will get to this proof eventually. It might take a few more lectures, but we will prove that the Gaussian integers is a UFD, and then we can do a lot of neat stuff once we have that proof. Anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.